Welcome to the deep dive. You've given us these sources, and, well, our job is to dig in, cut through the noise, and really pull out the core knowledge you need.
And straight to the interesting stuff, the useful bits.
Exactly. Today, we're doing a deep dive based on the strategic report you shared. It's aimed at business leaders, tech strategists, financial pros,
Right.
and it tackles a really fascinating, maybe slightly, future-facing topic: the security of tokenized finance
Things like digital bonds, stocks, even real estate on a blockchain.
and the potential threat coming from, well, quantum computing.
Yeah, that's the core of it. Our mission here is to unpack this. We'll look at how quantum computers could potentially break the security that blockchain uses now,
Okay.
and then explore the solution they propose, something called post-quantum cryptography, PQC.
And crucially, what the report says people should be doing now: financial institutions, tech leaders.
Exactly, what actions to take today. And yeah, we'll try to make the technical terms make sense.
Excellent. So let's start with the basics. The report talks about today's locks. When we talk blockchain security, Bitcoin, Ethereum, these new tokenized assets, what math is keeping things safe right now?
Well, at its heart, blockchain security relies on cryptography, which, basically means using really complex math problems.
Problems that are easy one way, but super hard the other way.
Precisely. Easy to set up the lock, almost impossible to pick it without the key. These locks secure your wallet, verify transactions, keep the whole ledger intact.
And the report focuses on two main types currently.
That's right. One is RSA. The idea is actually pretty elegant. You take two massive prime numbers,
Huge ones.
multiply them together, you get an even bigger number. That big number can be public. It's part of your public key, like your digital mailbox slot.
Okay, and the security hinges on the fact that even if I know that resulting huge number, figuring out the original two primes that made it is just computationally brutal for a normal computer?
Brutal is a good word. Millions of years, kind of brutal. Easy multiplication, incredibly hard factorization. That's RSA.
Gotcha. And the other big one, the one used more often in crypto wallets.
That's elliptic curve cryptography, or ECC.
Mm-hmm.
Bitcoin, Ethereum, most modern wallets use this.
Right. The report mentioned curves on a graph. Sounded a bit abstract.
Yeah, it can be. Think of it like this. You got a specific mathematical curve. You start at a known point on it.
Okay.
Then you do a sequence of hops along this curve, following specific rules. Going forward, doing the hops is really fast and straightforward if you know the starting point and the rules.
Makes sense.
But if someone only sees where you ended up on the curve, trying to figure out your exact path, how many hops, which direction, is basically impossible unless they have the secret info, your private key. It's like a mathematical one-way street.
Ah, okay. So RSA relies on factoring being hard. ECC relies on retracing steps on this curve being hard. These are the locks for now.
Exactly. For now is the key phrase.
Because quantum computing enters the picture, how different is a quantum computer? It's not just a faster laptop, right?
Oh, fundamentally different. It operates on quantum mechanics principles. Instead of bits being just 0 or 1, it uses qubits,
Qubits.
which can be 0, 1, or kind of both at the same time. That's superposition. This lets them explore a huge number of possibilities simultaneously.
So instead of checking answers one by one, they can check vast sets of potential answers all at once for certain problems.
That's the power, yeah. And unfortunately, that power lines up perfectly with the weaknesses in those current crypto locks we just talked about. The report points to Shor's algorithm.
Shor's algorithm, I've definitely heard that name. Developed back in '94, wasn't it? What does it actually do to RSA and ECC?
It's like a skeleton key designed specifically for those types of math problems. Run Shor's algorithm on a powerful enough quantum computer, and it finds a massive shortcut. It can factor those huge numbers for RSA, and it can solve that find the path problem on elliptic curves for ECC really, really fast.
How fast are we talking?
What takes a classical supercomputer maybe millions of years could potentially be done in hours, maybe even minutes, on a future large-scale quantum machine.
Wow. Millions of years to minutes.
Yeah.
Yeah, that's a game changer. And the report puts the time frame for these machines at maybe 10, 20 years out.
That's the estimate, yeah. It's not tomorrow, but it's on the horizon.
So if these machines arrive, what are the concrete risks for tokenized assets like those digital bonds or stocks?
Well, if Shor's algorithm can break the ECC or RSA, protecting your private key, then someone could potentially figure out your key.
Which means
They could forge your digital signature, authorize transactions from your wallet that you never made, steal your assets.
yikes.
Depending on the blockchain, maybe even mess with past transaction records, though that's generally harder. But stealing assets and faking transactions is the big, immediate threat.
And if you can't trust who owns what or that transactions are legit.
The whole system breaks down. The report is pretty clear. It could shatter trust in these tokenized financial markets. Their entire value proposition rests on that cryptographic security. Break that, and the market loses credibility.
That's incredibly serious. Is there a fix? Or is this just an unavoidable problem for blockchain?
No, definitely not unavoidable. That's the other side of the report. The solution is already being developed. Post-Quantum Cryptography, or PQC.
PQC. So new kinds of crypto that even quantum computers can't break.
Exactly. These are based on different mathematical problems entirely. Problems that are hard for today's computers and, importantly, seem to be hard for quantum computers using algorithms like Shor's, too.
Okay, so different math. What kinds are we talking about? The report mentioned a few.
Yeah, one major area is lattice-based cryptography. The report's analogy of a 3D brick wall is actually quite good.
How so?
Imagine this incredibly complex high-dimensional grid, like points scattered in space, but in many, many dimensions. Finding a specific point, or the shortest path between points in this lattice, turns out to be a really hard problem.
Hard even for quantum computers.
Seems like it. They don't appear to have a Shor's algorithm equivalent for this kind of problem. The report mentions names like Crystal's Kyber for encryption and Crystal's dilithium for digital signatures as examples.
Interesting. A different kind of mathematical hardness? What about hash-based signatures? The report called it one-way shredding.
Right. Hash functions are like mathematical blenders. You put something in your data, it produces a unique fixed-size output, the hash or shreds.
Easy to make the shreds, easy to check if shreds match the original data.
But impossible to reconstruct the original data just from the shreds. It's a one-way street. SVIN-CS Plus is a hash-based signature scheme mentioned, and it's already being used in some experimental quantum-safe wallets.
Okay. And then there were code-based and multivariate systems too, briefly.
Yeah, other promising avenues. Code-based methods use complex error-correcting codes, the kind used to ensure data transmits cleanly, but sort of run them in reverse to create hard mathematical problems. Multivariate systems use complex equations with many variables. The report kind of describes them as digital mazes, structures so complex that even quantum computers struggle to find their way back through them.
So we have these potential PQC solutions, these new locks. How do we actually get the whole world of blockchain and tokenized finance to switch over? What's the transition plan look like?
It's definitely a process. The report highlights a few practical steps. First off, quantum-safe wallets.
New wallets using the new math from the start.
Exactly. New users could start with wallets built on PQC, generating quantum-safe addresses and signing transactions securely right away.
Okay, that covers new stuff. But what about the huge existing blockchains like Ethereum?
That's the big one, upgrading the core protocols. Major players like the Ethereum Foundation are deep into research on how to swap out the old signature schemes, like ECC, for PQC ones.
Sounds like major surgery for a network.
It is. It would likely involve complex network upgrades over time, carefully managed, similar to other big protocol changes they've done, but focused specifically on this cryptographic transition.
And during that transition, the report mentioned hybrid approaches to avoid breaking everything.
Absolutely. Hybrid systems seem like a really practical way forward. For a time, transactions might be signed using both the old method, say ECC, and a new PQC method.
Like double locking the door.
Pretty much. It keeps things working for existing users and systems, backward compatibility, while adding that layer of future-proof quantum resistance. It bridges the gap.
Makes sense. Are there projects already doing this or planning to?
The report points to a few. There's quantum-resistant ledger, QRL, which was actually designed from the ground up for this. Algorand is mentioned for having an architecture that makes adding new cryptographic layers easier.
And the big ones.
Ethereum Foundation, as we said, is heavily researching it. And Multiverse X, which used to be Elrond, apparently has plans for hybrid systems too. So the work is happening.
Okay, so we have the current situation, the looming quantum threat, the PQC solutions, and a path to transition. Let's connect it back firmly. Why is this so critical specifically for tokenized finance?
Because tokenized finance, digital bonds, stocks, real estate titles, is all built on trust. Trust in the blockchain's record of who owns what, and trust that only the real owner can move those assets.
And if that trust is based on math that quantum computers can break?
Then the whole foundation crumbles. Imagine someone faking a signature to steal your tokenized bonds, or hacking a smart contract that manages millions in tokenized assets. The report stresses this wouldn't just be a technical issue, it would destroy the credibility of tokenized capital markets.
So it's an existential threat to that specific application of blockchain. But interestingly, the report also mentioned that quantum computing isn't just a threat, it could also be an opportunity for finance.
Yeah, it's definitely a double-edged sword. While quantum computers threaten today's security, that same computing power could revolutionize finance itself.
How so?
Think about running incredibly complex portfolio optimizations almost instantly, or simulating financial risk scenarios on a scale that's impossible today. Even verifying complex smart contracts could become much more efficient.
Huh. So if we manage the security risk with PQC, the very technology posing the threat could actually unlock massive benefits for the financial industry later on.
That's exactly the idea. Making the move to PQC allows the industry to navigate the threat and then potentially harness the power.
Right. Which leads perfectly into the final part. The action plan. What does the report say institutions, developers, regulators should be doing now?
It gets quite specific. For banks, asset managers, anyone dealing with tokenized assets,
Right.
start by auditing your current blockchain use. Figure out where your quantum risk exposure lies with these products.
Know your vulnerability. And for the tech side, the developers building these systems.
They need to get their hands dirty with PQC now. Start testing these new algorithms, figure out how to integrate hybrid security into their platforms. We're moving past pure research into practical implementation.
What about regulators? Do they have a role here?
Yes. The report suggests they should support the standardization efforts for PQC, like the work NIST is doing in the U.S. And they should start thinking about timelines, maybe even mandates, for adopting PQC in critical financial infrastructure.
Setting expectations. And finally, the tokenization platforms themselves.
They need to be smart about which blockchains they build on. Choose networks that are actively working on PQC and have a clear roadmap for quantum resistance. It's about building on a foundation that's ready for the future.
Okay, that lays out a pretty clear path. So wrapping this deep dive up, the core message from this report seems to be quantum computing is real, it's coming, and it poses a serious threat to the math securing today's blockchain and tokenized finance.
But post-quantum cryptography offers a viable defense. And getting ready for this shift isn't just about avoiding disaster, it's also about positioning the financial industry to potentially use quantum capabilities down the line.
And the urgency is clear. The time to act, to prepare, is now well before the threat fully materializes.
Absolutely. You don't wait for the storm to hit before you reinforce the roof.
It really makes you think differently about technological timelines and risk. Okay, so final thought then. If the industry successfully navigates this massive shift to PQC, tackles the quantum threat, what might be the next big fundamental challenge lurking out there for digital assets and their security? What comes after quantum?